and it's time for questions. Questions or comment or anything?
So I'll ask a question then.
Yes, thanks.
Okay, so I mean, getting this analog, you assuming some kind of stationarity, or that you can find images that have similar pattern, right?
Yeah, there's two questions there. There's the representativity and the stationarity. So what we assume is that the training image is representative of the process we want to model. For example, I showed the example of a braided river. I'm assuming that the training what I'm dealing with is a braided river, and my training image also represents a braided river, and have the same scale, and I make sure that they represent the same type of process. Then stationarity, we have many ways of dealing with non-stationary domains. And this is mostly through covariables. For example, if you have a domain that has a certain anisotropy or certain types of patterns of proportion of categories that vary in space, so it is non-stationary, we can generate from this a stationary image. For example, you have a training image that is non-stationary. You can also generate realization that non-stationary, but different. If you have information about non-stationarity, you can say which part of the training image belongs to which part of the simulation. You can do the other way around. You can have several stationary training images, translate this into one non-stationary domain with partitioning. So there's a series of strategies that have been developed to deal with non-stationarity. But if you're not representative, if you have the wrong training image, then it's game over. We say you cannot use MPS, everything will be wrong.
Right. So what would you say are the main limitation of this approach, if any?
Yeah, the number one limitation is really finding the right training image. If you have a big and rich training image that represents your data, you can do a lot of things. Because it's like a gold mine of information you're sitting on. And anything you will do that doesn't exploit the complexity of that, it's a bit of shame. You don't use all this pattern and all these things. If you fit a simple model to that, you lose something. But if you don't have this rich information, you cannot create it out of nothing, right? So it's really I would see MPS as a category of spatial methods, especially for big data. Big data, I mean big prior data. You have a satellite image that gives you a lot of details. So this is the main limitation. The other limitation I mentioned, the parameterization or the computation, these are like technical limitations that we can overcome. But the lack of a training image is a fundamental limitation that I don't think we can do much against that.
Another limitation is that we are on a grid. We need always to be on a grid, and sometimes it can be an issue. Not always, but sometimes it can be an issue. Especially the training image need to be relatively full from data from on a grid, because in other case we don't have enough data to find similar patterns. So we're coming back to the training image issue.
Okay, and the example presented are essentially spatial, but you could do the same thing in space and time.
Yeah. Oh, there's no technical problem. Then maybe it's harder to find the training image, although we have examples of, for example, we have this with the climate model. We want to downscale a climate model, and the climate model gives you an output every hour or every day. And if it's every hour, especially, there is really a temporal correlation between 1 hour and the next. The whole image are correlated in time and also in space. So you can design a MPS problem where you have a training image in space-time and you have a simulation also in space-time. Then you have additional challenges because then everything is non-stationary. Because in a climate model, you are at the scales you deal with, you have continents and so on, and it's very non-stationary. But we have some case studies where we did that. So it's a bit a complex setting, but you can do it in space-time. Yeah? There's no fundamental limitation.
In the case of satellite, I mean, what you had with the gaps, basically the satellite, I mean, one band is a different time than the next band, right? So if
no, in this case, it's all synchronous. You have just one image.
Okay.
All the bands are taking, you starting passes and records 5 bands. And
Yes,
you reconstruct the 5 bands at the same time. But the thing is that the spatial correlation between each band is different. So if you look just at each band in isolation, they will all have a different spatial correlation. But here, since we use the 5 of them at the same time, they inform each other. So once you put one pixel of one band with one value, you constrain all the other 4 and all the neighborhoods of all 5. So then that's why you have to simulate all 5 together. And you could do the same thing in space-time as well. But that's a bit more challenging with satellites because every day or every pass of the satellite, you have additional uncertainties, like atmospheric conditions will change, seasonality will change, illumination will change because it's different time. So it becomes a bit messy. But in theory, you could do it.
Okay.
Okay, I have one question about the spatial resolution. When you do the image training, can you use different types of spatial resolution images? They have to match.
Yeah, the training image and the simulation should have the same resolution. Mm-hmm. Otherwise, I mean, we've done things where the resolution is different, but then you assume some kind of scale invariance. For example, you take a training image of a process that is at a coarser resolution. That's what you want to simulate. You assume that there's a scale invariance, that the coarse resolution applies also to the fine resolution. So we try this. If there's actually a scale invariance, if you try on a fractal field, it works. Or something with an exponential covariance, you can actually reproduce a process like this because you assume that all the scales, you have the same process, the same spatial properties. But I mean, in the general case, you make the assumption that the thing you simulate has the same resolution as your training, because you really look at arrangement of patterns, and you say, okay, this same pattern is my training image, so in my simulation.
The question was maybe about using a secondary variable with another resolution, no? Because this we can do. Not all variables need to have the same resolution, but one moment or another, they will need to fit on the same grid. So we need to do whatever trick to fit them. Like, for example, we can have, I don't know, 20-meter and 10-meter resolution data. We just put only one data over 4 each time for the 21, and we can do that. But if you have like 11 and 10, it starts to be nasty, for example, if you want to take properly in account. But usually if it's only 11, 10, you can just interpolate and put them together.
Yeah, that's like you can really include covariables that are coarser. That's a bit what I showed in the example of the 2 different sensors, one high, one low resolution. For the high resolution, we have also the low resolution. But for the area where we have the high resolution, we also have the low resolution for the same zone. So we use the relationship between the two to generate the high resolution somewhere else. So you can use covariables, but the variable you simulate and the resolution you simulated as the same resolution also has to be on your training image.
Yeah, so I think another question kind of related to the spatial resolution. I know some applications like downscaling, you require this finer resolution. For example, the sum of those values agree to the coarse resolutions. For this algorithm, do you have similar applications?
Yeah, so this is more difficult. So basically what you say is that, for example, you downscale, you want that if you have 4 downscaled pixels and you average them, you fall back on the value of your coarse resolution.
Right. That
you have this exact correspondence. So this we can do it, but it has to be seen as a constraint in the distance function. Now, at the beginning, I showed this distance function. You have a pattern, you compare to another pattern, you want them to match. So what you have to do is a penalty term in this distance that says, if I don't respect this block averaging, I'm going to penalize. So I'm going to try to sample pixels that help me get to my correct average. And this can even done iteratively, such that in the end we arrive exactly to reproduce the average. We have a paper on that. I mean, the algorithm becomes a bit more complicated, but it's totally possible. It's called the block MPS.
Yeah, I think because some of this very detailed structure your algorithm can handle, it's possible, for example, you do Gaussian process prediction for the coarse resolution, then within each pixel, if you have other training data set and simulate a high resolution locally, it will be like combine two models to provide high resolution simulations.
Mm-hmm. Yeah, that could be used very well, actually. I mean, there's many ways to do it. If the challenge is really if you want to have exactly reproduce your mean, this is when you have to really put a penalty term in the distance function. If you want to approximately, if you want to just use it as a covariable that guides the simulation, it's much easier. You just use, like we said before, a covariable. Mm-hmm. But yeah, that's right. We could use two scales, one with the Gaussian process, one with MPS.
Right. Yeah, that might be a good combination. I think Gaussian process, as you said, cannot handle this very complex texture in the spatial field for small scale predictions, right? Yeah, your algorithm mainly used for simulations, like simulations, not exact prediction, right? I guess you can do that too.
Sorry, this you mean what?
So I think your goal is to reproduce the statistical properties. Mm-hmm. Right. But I mean, like, for time series, do you also do time series forecasting, for example?
No, I mean, we could do, I think Fabio, you played a lot with that, the short-term forecasting. You could do it. Mm-hmm. The problem is that there, in general, short-term weather forecasting, physical models are always better. My experience. Yeah. You can, it's hard to beat that. But we can, I mean, it works, but it's more interesting for the, I would say to reproduce statistics, because this is what it's really good at. But there could be applications where you just basically look at patterns and you make a short-term prediction. Yeah. Okay.
Just one last comment. I think during your presentation, I noticed this distance, all these measures, feel a little bit similar to this spatial generalized variogram. So
which
like
example
the
you mean?
variogram is defined as the pair distance square those increments. I think there was a version of generalized. Basically, if you have a regular spaced locations, you can apply different filters. Then this spatial variability is defined as the sum of those linear combination of neighbors square. Mm-hmm. It's as a summary of the spatial variability. I don't know if there's a link with this kind of distance measure. With
in all this would be also, you also look at pairs of data. So you always look at 2 points.
For traditional variogram, 2 points. For this generalized version, is a filter. You can define a neighborhood like 4 or even bigger. You can consider a linear combination of those neighbors.
Yeah. So okay. So it's based, but you have to define the filters as well.
Right. So you typically can apply many different type of filters. Mm-hmm. Yeah. So I think, I don't know if there's a like distance measure can be linked or can be used like borrowed from your algorithm. Yeah. Just one comment when I look at your presentation.
Okay. No, that's right. There's been also a lot of work with MPS method based on filters. So there's been, I mean, over the years, there's been many algorithms developed for MPS, and some of them involved, especially not only for categorical variable, also for continuous variables, to classify all the patterns according to filter scores, and then simulate the filter scores. And for each filter you simulate, you go back to the pattern. So it was not using variograms at all, not generalized variograms, but something based on filters. The problem is that you have this definition of the filters, which is always a bit difficult, because you have to make an assumption on what are the important directions, important patterns. You already start to assume that. And the problem is that it's an additional level of parameterization, and it's a lot of buttons to tune. So this was a bit difficult, and computationally also a bit harder. Yeah, it makes the whole thing more complex. But yeah, that's definitely something to look at.
Okay. Yeah, thank you very much.
Thanks for the questions. Other comments? So I see comments in the chat, although I cannot get there.
Yeah, Grégoire, we were talking about the extent to which we can explore distribution by just sampling patterns.
Mm-hmm.
And yeah, that is another typical limitation, is that if we don't observe a value in the training image, we cannot extrapolate that value. So this is negligible for many geological applications, especially the categorical ones. But for some other application, for example, for weather generation or things like that, where we are actually interested in sort of having a certain representation of the extreme, this can be an issue, because like we don't have a distribution where we can actually extrapolate unobserved value. And but usually this is also a main limitation for generic rainfall generators like weather generator. And in fact, there are like specific statistical models that are focused on generating and simulating only the extreme value. So it's a sort of like, it's a little bit of a subject on its own.
Yeah, but I agree with the comment also of Huang, that MPS is only for certain applications. So clearly you need to have repeated patterns in your training image to be able to use it as a training image. Yeah, example is if you have a training image, it's just one line. It's not stationary. It's not, nothing is repeated. You know, it doesn't work. You need to have some repetition. It needs to be large enough that you can repeat complex patterns that are diverse. You can repeat it enough times. So this is really, if you don't have that, you're going to be in a bad position to, you're going to have to go to other frameworks, basically.
Yeah, exactly. It's in that case, it's better to step back into a more parsimonious algorithm, so that you will have less complex structure preserved, but it will be more robust on using less data.
Mm-hmm. Okay, so I see Matthew goes directly in the next step. So, Matthew, maybe I give you the talking stick.
Okay. Yeah, it's look like a rate of question decrease, so I take advantage to switch. So I don't know if it's big enough for everyone. In the case, I can change the resolution of my window. So we prepare a Jupyter notebook, as we say at the starting, where I give you the link in the comments, so you can all check in the conversation. So that's the GitHub. It will stay after. So if you want, you can come later and play around again with it. And so today we will use it through Colab. Colab is a service from, let me first maybe explain before clicking. Colab is a service from Google to write Python and machine learning code directly on their server and use their GPU to do the computation. And so we will use this. So we have a small link here to open straight away in Colab. If by accident it doesn't work, let us know and we will give you directly the link of this one. I can do it straight away. Let's do that. So if the first link doesn't work, with the GitHub link, you can use this one. We will directly open in your Colab. So I just press on the link and I have it. So if anyone has an issue, let me know, that we can investigate and quickly fix it for you. So we will have multiple parts today. So the first one is about installing the all the material is globally just press the button, and I will explain what is going through, but it's nothing very essential for MPS. After, I will go quickly through the basic concepts. After, Fabio will explain more about time series and like what we call 1D examples. And I will finish with some more advanced and multivariable simulation on 2D data, remote sensing. It will give some multivariable too in 1D from Fabio too. So let's start with the installation. Oh, by the way, if anyone has an issue, don't hesitate to say it in the conversation, or even just put a microphone and complain, that we can go all together forward. So I invite you to all to install first, to go to this page, maybe waiting like a minute or so that everyone reads this point. And after,
maybe one thing to say is that you can deploy any of these. It's like you can open any of these triangles.
Yeah,
and,
we
see
can
everything that is inside.
Open each section, yes, definitely.
So the first section, you don't really have to look what's inside, because it downloads the code of the quick sampling algorithm, and it downloads all the dependencies, it compiles it on the Google machine. It does all this housekeeping that you don't need to care about. And the rest is really running the code, and with the example, with the data, with the parameters. And this one you will have to look at in detail. The first part, you can just run it, and then each of you has a machine in Colab. You have one processor, one GPU, and you can play with it as much as you want.
In the limit of 12 hours, I think. Okay. So you can just press this one, but for I will still explain what is going on. So I will go for each section apart, but you can definitely run the whole section together. So the code is divided in two parts. One is the interface that is like for Python, MATLAB, R, or whatever. It's just a small code that communicates with a server that will run the computation. So why we did this is that everyone can use the same code, whatever is his favorite language. I mean, some people prefer Python, some prefer MATLAB. We don't really have religion here, so feel free to do whatever you want. And the server is code in C and is highly optimized code. So it's much more performant than if we would have like integrated directly in Python, where we have like restriction to make it compatible to everyone. The server can be installed on Linux, Mac, and Windows 10. So under lower version of Windows, if you want to install it, you will need to use a VM. But I assume that today, more or less everyone moved to Windows 10 or 11 soon, when it's coming. So yeah, let's start. So first section is to, so you will maybe have like a warning. I have it in French because I have the browser set up in French. Just say that the code is on GitHub, and so it's not yours, can be dangerous, but just press run it in all cases. So the first part is to install the interface. So we make it simple, and so we just like a pip install G2S with the important. The libtif is for something later, but that's what is needed to install the interface. And this is just to check that everything worked well and didn't crash. It's not really relevant for now. We will re-import it later for run the code, but that's a key part of Python to use the interface. So after, we need to install the server. So the server will take all the requests of that any interface send, do the computation, and send back the result. So all the code is on GitHub, is free. Feel free to put comments, complain, add improvement, add your own code, whatever you think it's relevant. So we just like clone it, and after we compile it. So we have like small script to install it. So it's just like a simple make to compile. And before, we have some flags. So these flags are specific for Colab, because we don't know in advance which type of GPU we will get. So the compilation code can mess up and compile for a platform that is not handled. So I just say, okay, compile for all platforms. Is to take in account like CUDA acceleration. So that's probably the longest part. After the server, I just continue to explain, so we need a little of time. So after we will run the server. So the server has a daemon mode, so we just run it once in a terminal, and it will run in background from your computer. So either you kill it if you don't want it, either you don't put the -d if you want to keep control. If you are on your own computer, and you can keep a terminal open with the server on. Here it's not important because at the end we will just close the browser and Google will take care of removing what is needed. So when you reach this part, basically everything is ready to use. So we just like run some quick tests to check that everything is well installed. So here we just import NumPy and Matplotlib to like plot stuff. So we load a TI, and we have an echo mode. So it's just to check if the interface is working correctly. So it just sends the image. Yeah, TI is a training image. Yeah, definitely need to be said. And it just sends the image and get it back. So as you see, just at the training image we loaded here, it's just to see if the communication work well. So if anyone reach this point and already have like errors, let us know, because nothing else will work if this didn't work. So this still didn't include any simulation. So we'll do a small simulation to check that this part is working too, that the simulation code is working. So of our test, we never had any issue on Colab on any of these parts, but we never know. So this code is run on the CPU. So everyone get like 50% of a CPU with Colab. That's pretty weak. So it takes some time. I mean, if you do it on your own computer, it's probably like 1-2 seconds, but on Colab is more. And that's the training image and the simulation. Again, if you reach this point and you still don't have a simulation, let us know.
Yeah, one comment, if I may. So here you have half a CPU, but if you use it on your own computer or on your own cluster, it can be scaled to any number of CPUs, right? So I think you mean the test matter, there's no point where you really lose efficiency. The speed up is quite linear. So
yeah,
if you have 100 processors, you're in the game.
So we have a specific machine here with like 256 cores as CPU, and it's like linear. The only restriction is if you have like small simulations, then you have like conflict between dependencies of pixels, and so you are waiting one moment that the other pixel is simulated, that you have the value to compute the next one, and so that's the restriction, and that will limit parallelization. But if simulations are big, that's usually the case when you are looking for a lot of CPU resources. It's not an issue. And after a small example using a CUDA, I mean the GPU. So first line is just to check the status of the GPU. So here I have a Tesla T4. You maybe have another version. It will give slightly different performance regarding which one you have. If you have an error message here that you don't get like a 0 here and whatever name of a GPU, let us know. Something maybe to fix somewhere in the settings. And when we do the simulation, it should be much faster. So we will go through to explain all the parameters were in the command line to tell what do everything. And here again, we have a simulation with whatever parameters. At 5 seconds, definitely much better than the 30 from before. Okay, so if anyone reach this point and have errors, please let us know. So I will just pack it because it's not relevant for the coming parts, but feel free to leave it open if you want.
Just a question, Mathieu, can I?
Yeah, go on.
So did you change any of the parameters of the simulation? Because the result looks, I think.
It's possible if you run it again, it's maybe different. It's like very, I don't know, it should be.
Yeah, I know, but I mean, it looks quite different than the previous one.
And is the parameters are similar or not?
I just run the code, so I guess parameters were the same, no?
N equal 50, N equal 50.
The kernel.
Maybe you had the kernel, yeah. That's a kernel of 51 by 51 size.
Yeah, and the other one doesn't have, so that's the reason.
Okay, thanks.
So they should be identical if you have the same parameters.
I mean, two simulations are not identical, but should be similar.
Should be similar, yeah. That's in this case they're not quite similar. So
yeah.
Kernel that causes.
That's the kernel, yeah.
Okay, thanks.
That should be tuned to be a little better. So if anyone has an issue until here. So question, why k is a float number? We will come to this point straight away. So just import like all the library needed for the experimentation. Here you download the image which needed. So we have a repo on GitHub where we have like standard training image as TIFF. So it's very easy to load in a single line. That's allow us to make like code that we can just send to everyone, and all the resources are needed will be downloaded straight away from internet without need to provide like attached file to the demonstration and so on. So that's the training image that it was already presented before. I mean, maybe in the presentation it was tilted, but globally the same. And let's go for the first simulation. So in this simulation, so I will start first with the input parameters. We have like -a QS that specifies the algorithm, because in the G2S package, you have many algorithms, and this one we'll use today is QS. So all the day, you will just use this one as a chunk. After we put as an input a training image, that is the image source that is called here source. And after we need to specify the type of variable that we have. So that's DT for data type. And here we just put like 0. So we have code. So 0 is for continuous variable and 1 is for categorical. And you just provide an array with as many variable you have. So if you have 2 variables, is 0, 0. If you have like 1 categorical, 1 continuous, you put like 1, 0, and so on and so on. After we need to provide a grid that we want to fill. So here we will do an unconditional simulation. So we don't have points in advance in the grid, but each pixel that need to be simulated need to be filled with not a number, a none. That the algorithm know what to simulate, what is a value to simulate, and what is a value. We assume that no one wants to simulate nuns. It's a hypothesis. I would not see to what it's useful, but that's the idea. And in the training image, the range of value can be whatever you want. So we just create here an image of 200 by 200 and multiply by none to have an image only with none. After we use k, so in this case we use 1, so it's the best one that was explained before in the presentation, and the number of neighbors will be 20. That's the input parameters, and that basically is the minimum parameters that you need to make a QS simulation. If you have k or n with missing, it doesn't work. If dt is missing, it doesn't work. Same for the images. In output, we can have multiple output. So we have basics is a simulation. That's what we are interested. And after we have an index map, who let us know the position in each pixel. In each pixel, the position of the pixel in the original image. I will explain this a little more in detail, a little lower when we will use it. And after it gives other outputs that you can explore, look, whatever, it's in the documentation. Typically, you have the computation time. The computation time was provided here is a pure computation time only of the simulation. It doesn't take in account communication between the interface and the server, between the interface and the server. So it's usually the time we report in paper is a CPU time consumed. So let's run the simulation. And after we have like easy code of matplotlib to display quickly the result. So from before, we know that it should be take around 30 seconds to do the simulation.
In the meantime, we can also say that there's a documentation with all the flags to run the code, or the list of all the flags and things. Yeah, you have to, yeah.
Here's the documentation.
Yeah. So there's a documentation, there's everything about installing on your the server and everything, but we can skip that because we don't need to install it today. Maybe you can go down to the flags.
Parameter of QS. So yeah, it's just on the bottom. And so like here you have all the possible parameters that are supported in the current implementation. Coming soon are usually available, but are a little more risky to use. Experimental again is like when we were not convinced of the result of the added value, but because it's implemented, if it's useful for anyone, feel free to use. So yeah, that's all the parameters, and you have some example at the bottom too. But probably the demonstration from today is like even more useful than these examples. So now it should be finished. Yes, it is. So the first question is, what is this influence of this n over the simulation? So you can, for example, change the value. That's why we did that today. Let's put more, put 80 to see the results. Feel free to play around and to check with your own numbers what's going on.
Maybe you could do this with the GPU version to go faster.
Yeah, we're just on 30 seconds. It's not like really critical. Later on the bottom one, definitely. Because so the training image here is like 200 by 200 and simulation of 200 by 202. So it's pretty fast. No reason to have the same size. It's just a trend. So we see that we have like patch of similar pixels and stuff like that. Yeah, remember why here I put a small value. So on the 21, you don't have that. And here you have a simulation with like k equal 2. So that means we use like one of the two best results. And we put like N300. That's crazy big value for such simulation. And so basically we'll try to copy paste always the same situation, because we will not really, it will try to find exactly the 300 pixel in the same setup, and that's extremely hard, but still he will try. And after we put to add variability that we don't have a pure copy of the training image, we put k equal 2. So we still like introduce some variability by sampling one of the two best candidates and not having a pure copy of the image.
Yeah, that's related to the question. That's related to the question that you asked before, Mark. If you have an n of 300, means that you have 300 neighbors, and there's no reproducibility. You will never find twice the same pattern of 300 pixels. There's no way in a small training image like this. So you will find each pattern only once. So it means that you simulate one pixel coming from one part of the image, and then the neighbor is going to be the neighbor in the training image. And you're just going to rebuild the same training image again because you have no variability. So the best possibility is just copy and paste the whole training image.
Yeah, and here, even with k equal 2, we globally take the neighbor of the best, because it's often the best, the neighbor of the best. And so we have this small scale noise as output. So that's typically something you shouldn't do. Just to come quickly to the question that was asked before, why k can be a float number. So k can be interpreted in different ways. So one is one of the k best one of the I mean, 1 is the best one, 2 is one of the two first best one, and 3 and so on. But we can see it on the other way around. It's like if we scan the whole image and we put k equal 1, okay, we take the best one. But if we take k equal 2, it's like if we would only have like scan 50% of the image and take the best. And k equal 3, again, we could have like imagine scanning only 1/3 of the image and taking the best over the third we scanned. And so by continuity, we can find our rules, like saying like, yeah, but I want to scan like 75%. I am not interested in like in 50 or 100. I want something else. I want 2/3. And 2/3, for example, if we get it the rule back, is like taking one of the time, like in 50% of the time. Let me don't say something wrong. So if we want to scan like 2/3 of the image each time, it will say that for each pixel, either we take the best or the second best, but only 50% of the time we look for the two best. So if we do the cumulated, I'm not sure to be clear. If we do the cumulated, we have like 60% of the time we take the best one and 66%. And for the 33 other percent, we take the second best one.
It can also be interpreted as a quantile value, isn't it?
Hardly, because it's to relativize to the amount of pixels that you have in the training image, so it will change for each training image. Okay, it's a proportion in the training image, but yeah. So no, ironically, k larger is slower, but is highly insensitive. I mean, our test shows that if k is not 100, you don't really see any speed difference. What is to know about QS regarding some other algorithm in MPS is that it will give you the result always in the same time. Whatever the parameterization, except for parallelization, if you are looking for n equal 300 on a small simulation. But if we say normal settings, you will have always the same time for the computations that we can predict. In fact, you can just run a small simulation and just multiply by the number total of pixel to do, and you know the time it will take for the complete one. And so, yeah, k larger doesn't speed up stuff. So reducing quality usually don't speed up the simulation. So no interest to do it. So let's move a little forward. So now we are coming in this question of the second variable, that is this map. We say where the pixels were taken. So the simulation here that I plot is this one, where we see that we don't really have patches that were copied from the training images. Locally, we see some micro patch, but globally it's different. And this one where we clearly see like huge patches that are just stolen from the training image. And this is reflected in this verbatim copy map, where we see that we have a noise on one side. That means we one moment take a pixel from one position, one from another position, and that's what we are looking for usually. And on the other side, we have like a map where we see that we have like basically 5 big patch that we just steal corner of the training image and try to fix in the middle, that we can definitely see by this noise of trying to fix in the simulation. So usually we want something like that and not something. Do you see my mouse? I don't know.
Yes.
Yeah. Okay. So we try to have something from on the left side and not from the right side. Next part. So that typically once output we check to check simulation quality. So we explained during the presentation that we can weight each neighbors to increase or reduce the weight, so the importance in the matching. So you can visualize this as the following one. So we have the training image on the bottom, which one we are moving our pattern that we are looking for. And each pixel regarding the distance, we can put a coefficient to give more importance or not. So we provide this information through in QS using a parameter which is called the kernel image, which should be always centered. So if you're only looking on, if you have, for example, a time series and you are looking only on the past because you want to do that, whatever the reason, you still need to center the kernel. That means that the center pixel is the pixel you will simulate. If you're not interested in any other pixel, you will need to put 0 as weight for them. And so they don't will have any importance in the metrics, but still you need to be centered. So when we run, when we provide this pattern, all the weight, all the kernel, I mean, all the pixels outside of the kernel are considered as null. So we just put like in a hard way in the code 0 there, but in fact, it's just by even not taking them in account when we do the search, because we know that they don't have any importance. So simulation should still take around 30 seconds. So regarding if you have like maybe university account, it go a little faster because Google is a little more generous with some people than others. And that's the output we get out of the simulation. So we put k equal 2 here. If you put like k equal 1,5, you will probably get something a little more connected in the output. Feel free to play around with the parameters and the kernel. You can change the size too. So typically here we put like 51 by 51. That means that the biggest pattern that we can take is 51 by 51 pixels. So that should be something like that. The image make 200, so it's like 1/4 in the size of in the length of the image. And so the algorithm will struggle to make long-range correlation. For example, you cannot get like a 100 pixel correlation because the pattern is just too small to do that. So here we just create a pattern of kernel with like a radial. So that's a small trick to create like a radial pattern. So we generate a 0 that we pad with one value of by adding like 25 values of 1 on each side. And I think it is SciPy who provides this function that allow to compute the distance to the closest 0. So we just have the distance for each pixel in the image of the closest 0, and after we just like put like a exponential negative of this one. Do I plot the kernel? In worst case, I can just add a cell maybe to plot the kernel. Yes, it's a good idea. Let's put the kernel in color. So that's the kernel is just the digit. So you see that in the corner is where is the lowest value. So it's almost only 2% comparing to the center. And that's how visually we see it. So the pixel very close to the center are very important, and this one very far, very not important. In fact, when we have only few neighbors at the starting, they are still important because you don't have some with high value. But still, at this moment, we say that we want still local continuity. So even if we match all the other perfectly, this one with the neighbor need to be logical with which one we are currently simulating. Because if the path is random, we don't have guarantee in which order they make, and we can accidentally simulate 2 neighbor pixels at the starting. So typically tend to improve the simulation if we have the good kernel. After, what is a good kernel is highly dependent of the training image, and it's a whole study by itself. So that's for the starting about which parameter you need to know to be able to start to use it. And now I will let Fabio continue a little with the 1D series. So you can play a little bit. Yeah.
Before we just jump to the next, maybe we should just give a bit of time for everyone to play with the parameters in these examples, the N, the kernel, the K, just maybe to get a feel for people who aren't familiar with yours. And maybe we should take a very small break or so, because
that's a good idea. That's definitely a good idea.
Let's see each other at 2:45.
Yeah, in 15 minutes.
Okay.
For those different time zone. Is that okay? Can have a coffee in the meantime, and you can keep playing with the code. It should work for everyone. Otherwise, let us know.
See you later.
Okay, good.
Yeah, and if you have any question, don't hesitate to ask in the chat.
Okay, I guess we can start again.
Yes. So let's move to the 1D example, time series analysis and modeling block. Let me share my screen.
Maybe just if someone has a question, someone in the meantime tried a bit or encountered a problem or anything, has a comment. You can also use the chat. Huh? Okay, so nothing. Sorry, then go ahead, Fabio.
Okay, can you see my screen well?
Yeah.
Okay, cool. So just a little reminder is if by any chance you have left your collab session and you wanna run the 1D example block, you still need to rerun the install G2S and its Python interface block, because you need to rerun the server and everything. But if you have left your collab open, then it's all okay. So let's open the 1D example. We will show now an example which is basically on time series analysis and modeling, where we are generating multiple realization of our time series to explore the uncertainty in our data. So the first block, just import the packages, the G2S package and NumPy and Matplotlib and other cosmetic tools. So just click on run and it's all fine. The second one is it's where we define some function that basically generates and plots some statistics. So for example, the first function is the triangle function, just generates the triangular function that we have seen before in Gregoire's presentation, that indicates the position of a datum in the calendar, in the year calendar. And then we have some function to make comparison of the simulated time series with the training image, and other function like to make the histogram, to compute the monthly mean, and to make some statistics about the dry spells, which are like the period which are occupied by zero values. So I'll just skip on this part. If you're interested, you can go inside the details of the function, but they are just basically displaying function. So just run the block and it's done. So let's go down to the other one, which is the about data import. So we are working on a time series by the Governmental Bureau of Meteorology from Australia, and just run the code. And here is the time series we are working on. It's a daily time series, which is pretty long. It's a daily time series from Darwin. And it's particularly interesting, is sort of like a Lamborghini of rainfall time series, because it's super long. You can observe, like you have super intense rainfall observation up to 350 millimeters per day, which is a lot of rain. And you have a very marked seasonality. So every small curve that you see in the time series is 1 year of data, where we have super high rainfall in winter, calendar winter time, and super dry conditions in the 6 months later in the summertime. So those are pretty hard conditions to observe even, and also to model. So it's a perfect example for us. And then let's begin by generating multiple simulation. In general, why we want to do that, why we want to generate multiple copies of our data, is because we often want to study the uncertainty in our data. So, for example, we want to generate multiple possible scenario of our rainfall in Darwin over the estimated period. And we want to inject this rainfall into an hydrological model, for example, to see how the uncertainty is transferred to the physical processes concerning the hydrological model. So those are all things that we do when we want to, for example, make some engineering application for example, it estimated the droughts over a long period or floods. So this is a pretty normal routine application. So let me go back now through the QS parameters. And I will begin by already running the code while it takes a little bit of time to get completed, the simulation. So let me run the code. So we see here the message performing 10 time series simulations, and we are just generating them. So in the meanwhile, I will rapidly go back to the ingredients of the algorithms. TI is the training image, which is a time series. So in this case, it's over time, but it can be any 1D data. For example, for geologists can be well logs, or for climate scientists can be, for example, the trace of a weather balloon or other type of data. So here we just give R, which is the time series vector. DI is the data that if we have any data that we want already to place in our simulation grid. In our case, we run unconditional simulation, so no given data, and we just generate a vector which is empty like our training image. And we just multiply by NIN, which means basically that we generate a vector of NIN, which means an empty vector. DT, in DT, we just specify a flag for the type of data. In this case is 0, which means continuous data. Then we have the key, famous key parameter, which is the quantile threshold. So here we use 1 as value, which is basically, it means basically that we are gonna take the best over the whole training image. Usually the value that we use for K range from 1 to 3. Usually there are no fixed rules, but usually it's that range. Here we have used 1 because we have pretty hard statistics to preserve, and we have a long vector of data, many years of data. So we have a good chance of really going in the details and having a lot of pattern to choose from. So we want to be a bit picky, and we need to be because of the hard statistics to preserve. So key equal 1, and then n equal 20. It means that every pattern that we look for will be defined by the closest 20 data, which means basically the closest 20 informed days of rain in this case. And it is a parameter which is linked to KI, which is the kernel definition. Here, for simplicity, we are just using a uniform kernel, which means that we define a flat function, in this case of size 101, and we just assign the value. We use the function once, so it means that all the position will have the value, the weight 1. So it's a completely uniform. and it is 101 of size. It means that the central pixel will be the data to simulate, and then we will look back for at maximum 50 days and forward for at maximum 50 days. So 50 plus 50 plus the central pixel, 101. So it's a one-dimensional kernel because the time series is one-dimensional. And then S is just a random seed that basically allows us to repeat the simulation and get the same result. So we just put an arbitrary value of 100. And then JB is the number of threads to give the algorithm to work with. So we just give one because Colab allows just one CPU to use. But on your own machine, if you install G2S, you can use as many jobs, parallel jobs as you have available. And then an R finally is the number of realization. We just use 10. So 10 realization in our practice is a good number to make a quick evaluation of the variability. But usually for papers results, we use 100. So it's pretty arbitrary. You can run like convergence function to see whether you have reached a good statistical stability. You can increase the number of realization as well. So here is the code to launch the simulation. We just pre-allocate an empty matrix that stores for every column a generated time series and just messages and just a for loop where we increase the seed by 1 that has to be done to generate a different realization, some messaging, and the G2S function where we basically assign the same parameters we have seen before. And then we just extract the time series of the rainfall amount. So we are already around the code, 10 simulation completed. So now let's analyze our results. We run the code next code block. And we basically, here we are basically plotting two time series. One is the training image and the other is the simulation, one of the 10 simulation, and we compute the histogram, monthly mean, and dry spell histogram. So let's run it. And if everything goes well, we have the statistics. So first, visual comparison, that's the original data. You see seasonality, extreme value, and everything. And here is our time series. So we see that we somehow move in the same range of data, but we miss some very high extreme. And also the annual seasonality fluctuation is a bit distracted, is not really preserved. That's because we haven't given yet any information about the calendar. And if we look at the statistic, we see more or less the same type of results. So the rainfall frequency distribution is more or less preserved. So we see in blue the training image. So a lot of days with 0 rainfall, and then a good amount of days with until 100 millimeters, and then a few events of very high rainfall, like 200 and 300 millimeters. So the blue line is the training image, and then we see this small box plot that show the variability within the simulations. And we see that there is a small bias towards low values, so we don't always reach the target amount of days, but we preserve quite well. I would say it's quite acceptable as a result already. Conversely, if we look at the mean monthly rainfall, we see that we do not make any distinction in the year calendar, so the position is not tracked. for each day. So we see that we simulate no specific seasonality. It's completely flat, our seasonality, while it's very pronounced in the training image. So we have to do something to fix that. And here we have the histogram of the dry spell length. So it's the length of the period which are dry, basically. And see, there are a lot of very small, very short spells and a few long spells. And we sort of like, we leave the algorithm exploring this kind of heterogeneity, and we sort of preserve this variability. So if there are no questions on this part, I can move on to adding some auxiliary variables. Okay, I don't see any. Let's see the chat.
Fabio?
Yes.
Can I ask something?
Yes.
In your first figure with the title Daily Rainfall Frequency Distribution.
Yes.
Can we say that the simulations underestimate the reference data?
It's like I would rather say that there is a bias towards low rainfall, in the sense that it means, for example, if you see the bean on the 100 value, you see here 100, you see that the box plot is a little bit below. So it means that
I agree, but I mean also on higher values, we can see that the simulations go a bit under the reference value.
Yeah. It means that there are less days that have that value. So it means that that value can be present or not. In some realization, it's present, and some other is not present. And we can see it also from the visual comparison. You see here, this is the original data. You see there is a very high extreme, is the maximum actually in 150 years. It's over 350. And while here in this realization, there is no data like that, you see. So in some sense, it's true, like we are sort of underestimating the very extreme values, which is something which is pretty common if we just resample the values. So we have to do something to improve that type of statistics.
Mm-hmm. But also the low extremes or only the high extremes?
In this case, the low extreme are pretty, like you see at 0, we have a good amount here. Yeah, we sort of like preserve we are close, we get closer for the lower values.
Mm-hmm.
So,
okay. Thank you. Sorry.
No problem. This is already not so bad, I would say, but we can improve it. So let's define an auxiliary variable. So let's take the triangular periodical function that describes the year. So let's see how it looks. Sorry for the size of the figures here. We just have embedded figures. I could not find a way to make them pop out. So I'll just try to make it larger by zooming. So you see here, these two very fluctuate, very highly frequency curves at the base of the time series are the auxiliary variables. So they are basically triangular function that has the 1 year period. And this just describes the position in the year of each days. So this information is just regular. It's a theoretical function, is known. So we will just give it as conditioning data. We won't simulate it because we know that every day has its own position. There is no particular information in it. So we'll just give it as conditioning data. So how to do that? We take back the same script. We just change a couple of parameters. So here in the TI now is multivariate with 3 variables, the 2 triangular functions, which are also, of course, 2 time series, and the rainfall time series amounts. So we just use the stack function to stack the time series one over the other. And then we, now we, as DI, so destination image is the name. So basically it's the conditioning data. We just give the first 2 columns. You see from 0 to 2, which are the triangular function 1 and 2. So this will be given, no need to simulate them. And then we have specified 3 flag for the 3 variables, 0, 0, 0, so all continuous variables. And the kernel will be trivariate as well. So 3 one-dimensional kernel of the same side, 101 pixels. So here we just added the 3 here. So it's a 3-column kernel. And the rest is pretty much the same. So let's start the simulation. If you have any question in the meanwhile. Otherwise, I can just make a small commentary. So when we define an auxiliary variable, usually there are two ways of using it. The first one is to give the variable, is to give the data as conditioning data. For example, that's exactly what we are making here. So we know that there is a seasonality, we just give it as it is. Another case could be, for example, we have another type of data that is somehow correlated and can be predictive of the data we want to simulate. In that case, we can also give it as conditioning data in the DI array here. While there is a second way of using the auxiliary variable, which is to co-simulate it with a target variable. So it means that the variable will be informed in the training image, and it will be simulated together with our target variable. We will see an example of it in the next example, which will be also the last one for the 1D case. So here it's pretty slow because we are just using one CPU, and the time series is pretty long, but it works very well with many CPUs. It really gets much faster.
Yeah, actually, you have only half a CPU here.
Yeah, exactly, half. So it's even worse. Almost done. And another thing that we can say about it is that if you take a look to our papers, we propose some more complex setup for rainfall simulations. And for example, one trick that we use is that when we define a kernel, for example, in this case, it's a 101 days kernel, which means that we will span over like 50 days in the future and 50 days in the past. But This doesn't mean that we have to be limited to that, because we can, for example, define a secondary variable, an auxiliary variable that is a moving average, for example, that for each day gives you the average rainfall in its neighborhood, which can be 1 year, 10 years, or even more. So this variable will be defined, will be local, but it will be information on the larger scale variations. So this is a trick that we use, for example, to use a limited kernel, but to encapsulate information for a larger scale. So we have done the simulation. Here are simulations completed. Let's run again the results analysis block, the next one. So is the same statistics, just to see if we have improved. So yes, so here are the original data. And here is one simulation. You see that now there are two things that have improved, which are the extreme values have been preserved entirely up to 350 millimeters. And also the annual fluctuation seems to be quite well preserved, you see. So the rainfall frequency distribution is also better preserved than before, as you see. As you see here, the box plot are better centered on the reference. And also the seasonality is preserved pretty well. There is still a bias towards the lower values in the very extreme rainfall months, here in January, February. And the dry spell is also pretty well preserved. So let's do one last example where we had a second variable, which is basically, I just took the time series, the training image time series, and run a logical test larger than 0. So which means that it will be true when we have a wet day, and a 0, so false, when we have a dry day. So this is just this small variable that we have here at the base that takes 0 or 1 for every day. So I will begin by running the block for the simulation, so we will save time. So here, basically, I've just stacked another variable. So here in the TI, we have a stack of the two seasonality variable, the dry wet variable we have just created, and the rainfall amount. The dry wet pattern won't be given as conditioning data, but it will be co-simulated together with the amount. It means that we're gonna check two types of patterns at the same time. So the dry wet and the rainfall amount at the same time. And we are gonna also simulate the two variables at the same time. So the DI is just the two calendar variables. And we just increase the vector of data type flag of 1, 0. So it's true that in theory, it's a categorical variable, but it's a binary variable, just 0, 1. So I've been told by Matteo to use a 0 flag, so to treat it as a continuous variable. So I just trust him because he takes care about the implementation. So and it works. So I will just use 0.
So yeah, maybe I can say something about that.
Yeah, sure.
So yeah, in theory, 1 should work, but like 2 weeks ago, someone discovered that it give a bug sometime if we put a 1, that we have like the combination of continue and categorical variable. And I'm currently tracking the origin of the bug. And because it's only variable categories, definitely, I mean, binary, we can definitely use it as a continuous. It doesn't change performance, not at all, because in all cases, we need 2 FFT for each one. But if we have more categories, it can start to be complicated. And I'm I'm on the question of where is the bug and how to fix it.
Yeah. So if I well understood, Mathieu, it means that if I have more than two categories, I should put one.
Exactly.
And it should work fine if we all have categorical variables.
Yeah, maybe the bug is still affecting the problem. Until I find the bug, I cannot tell what the consequences. But it's like a recent bug. I mean, like 1 year ago, I'm pretty sure we didn't have it. So it's probably due to a last modification recently. But I'm tracking down to find out what's the reason.
No problem. And then, yeah, the kernel, I modified the KI, which is the kernel, is a 4-varied kernel. As you see here, there are 4 columns of 101 positions. And in this case, for simplicity, I just use a uniform kernel for all the variables. And you can use also a mixed kernels, so uniform for one variable, and you can use a decay function for other variables, for example. So it's up to you to test. I run some tests. Honestly, I haven't seen so much difference in case of rainfall. So I'm just using a uniform one in this case. So, but yeah, feel free to test. Yeah, and in the for loop for the realization, for the 10 realization, I'm just retrieving the 3rd column, which corresponds, so sorry, it's the 4th column because 0, 1, 2, 3. So 4th column, which is the rainfall amount. So I'm just extracting it and injecting it in the RSIM output matrix. Almost done.
Maybe while it runs, I can make a small comment. There were questions in the chat about the dimensionality of things. So the dimensionality of the whole problem is always the same. Whether it's your training image, your data, or your grid, the grid on which you simulate, it's always the same. So if you have, say, a 2D grid with 3 variables, everything is 2D with 3 variables. So your training image is the same, your simulation is the same, your data is the same. If you have one of the variables that is unknown in the simulation, it's full of nonce, but it still exists. The dimensionality is the same for everything. So your data also, your conditional data that you want to put in the grid, they need also to have it's a bunch of NaNs and just values where you do have values.
Yeah, and yeah, there are other type of implementation which are sort of developing in the latest years, which sort of like take into account data of different dimensionality. For example, the TI factory case or other types of applications. If you are interested in it, we can discuss it maybe in another seminar or privately. So because it's a bit more complex, but yeah. So yeah, it is completed. Just
a small stuff. Yeah, they need to have the same dimension. I mean, 1, 2, 3 dimension, and the number of variables need to be the same. But definitely, the simulation grid doesn't need to have the same size as the TI. Can be much smaller or much bigger. It will still work, and we can have multiple training image and so on and so on. So
no, you're at same dimensionality, not same dimension.
Yeah. But prefer to be clear about it.
Yeah, sure. No, yeah, it's important. The size of the data is important, especially in the climate time series, because you have like larger return time events. So if you have 100 years of data, which is already a lot, but you want to simulate, for example, even more, even a larger time series, you you have to take into account the fact that you won't preserve the extremes. You have to expect larger extremes than the one that you observe in your training image. So this is something which is a statistical limitation. Yeah, another thing to say, which is pretty useful, like let's suppose that you don't want to make several simulations, but you want to just fill in the gaps in your data. It's pretty easy to do. You just need to put here in the DI, instead of an empty grid, you just give your data as they are. So you just put a copy. You just write MP copy TI without the times NP none, without it. Otherwise, everything will become NIN. So you just give a copy of your TI, and the algorithm will just simulate the missing data. So the data that are marked as none inside the TI. So this is a quick way of making a filling in your data. So it's completed. Let's run the analysis to the last block of our part. So original data, again, simulated data, pretty similar to the reference data, and the rainfall amount distribution is pretty well preserved. The monthly mean has a bit improvement, but still lacking a little bit of definition in the very wet months. And the dry spell distribution is pretty well preserved, I would say. So that's all for this part. So with the script that we have shown here, we have seen how you can really explore the uncertainty. You can also gap fill your data if you want. You can stack up different variables, and this is an approach. Just the last comment to end is pretty interesting because it involves both the skills of the geostatistician, but also the background of the applied scientist, because it's not a trivial problem to choose the right data to stack up as auxiliary variable. It's really important to collaborate with the applied scientists to find the best setup, and the outcomes are not always trivial, like are not always easy to predict. So we have to make many attempts sometimes to find the good predicted variables, and there is a lot of creativity in the process as well. So it's pretty satisfying to work with this tool as well.
Fabio, may I ask a question?
Yes.
I'm wondering where is the gaps, because I think that you just simulated, yeah.
It's not this case. This case around, I just said that if you have some gaps in your data, you just give as conditioning data your actual data entirely. So if you go here and you want to make a gap filling case, I suppose that in R, which is the rainfall time series, you have some gaps. So it's sufficient to make sure that you have an NaN in the position where you have the missing data. Sometimes you have flags, you have missing data flags and stuff like that. So you just replace the flag with the NaN. So you will give the data as training image, and you also will give an exact copy of the training image as conditioning data. So it means that the grid will be already informed with all the data that you have, and the algorithm will only simulate where it finds NIN. So it's pretty easy.
Thank you.
Okay, so that's all from my side. Is there any question? I've seen you have already answered. Thanks. Okay, so if there is no other question, I will leave the lead to Mathieu for the last part.
I am back. if anyone has a question, don't hesitate.
I have just one small comment to make. I'm extremely ashamed that I forgot to record my presentation at the beginning. So to make up for that, I put it on GitHub, the PowerPoint. So we have a little GitHub repository related to this course, and I'm going to put it in the chat, the link. So it's part of the GitHub page of our group. If you go there, you can also find the repository of the Gaia UNIL, which is all our codes and everything. Okay.
I have also just a follow-up question. So I know you have a book with Jeff Cares in 2014, right, on multiple point geostatistics. Is there something more recent, or is there like a review or about the latest? I mean, to kind of see more details about the methods, or
no? For example, the QS is not in this book. It came out last year, but there's a paper, of course, on that, which describes everything, and it's an open access. It came out in Geoscientific Model GMD, Geoscientific Model Development, which is open access.
Okay.
And the link, if you go on the documentation of the QS, you have the link to the paper also.
Okay.
But a more recent review paper, no, maybe we should do it.
Yeah.
Like in
we have, so sorry, Fatime, we did a paper on review on the applications of MPS to remote sensing.
Okay.
So that's not really a review. That's a review, but it's not on the point of view of the algorithm and the method. It's really the application of this to remote sensing. But just on the methods, there's nothing really recent as far as I can.
In the IMG 50 years book, it gives one from Tamazabi.
Yeah, but it doesn't really. It's not really.
Yeah, it's not the most detailed one. It's not like the book for sure. It's like
on the handbook of mathematical geosciences, we did something that is a short review, but it's not really exhaustive. No, we don't have a new version of the book.
Okay, so the book is maybe the best if you want to, I mean, for our student to read some of the details and understand.
Yeah, you won't have the latest algorithms, but I think you can grasp the general idea. There's a lot of examples. So yeah, maybe starting in the book, there's section 2 that is really about the design of the algorithms. So if you read just the section 2 of the book, you don't have all the philosophical principles and the multiple examples, but you just really know exactly every step. For example, what your question before, how to deal with non-stationarity. So there's a chapter in that.
Okay. So I just saw from your website, so I just put in the chat the link, I think, to the book. So if some students want to read more about that.
Yeah, thank you. Yeah. And just to say, like, I know you can find online PDF versions of the book.
Yeah.
I cannot just send them around. I don't think I can do that. But if you search, you find.
Yeah, we probably have it in the library at KAUST. I mean, access in some way.
Yeah, probably. Yeah, it's widely.
Yeah. I mean, another general question I have is, I mean, you don't need to answer now, but maybe to think about if we want to interact in some way is, what are kind of big open challenges with this method that perhaps needs to be explored further and might trigger some interaction? And
one big one I can see is the characterization of uncertainty.
Yeah.
So this is because the uncertainty you have is going to be a mix. For example, what Fabio showed, the variability between realizations, you get an uncertainty. Okay, you can be happy because your data is really an uncertainty, but what does it reflect, this uncertainty? It's not based on a model. It's based on the choice of the training image, the choice of a specific algorithm, the choice of specific parameters, and okay, you get the variability. But what does it mean in terms of uncertainty? And this is something, I mean, we always have questions, and we always, I mean, we cannot give a definite answer because we don't have a proper model underlying that.
Yeah. Okay.
So yeah, we welcome input on that.
One note. Mama's note, yes.
Yeah, I have one question here, if possible.
Yeah, go on.
Let me give me a second. Okay, if you are talking about the MPI running this on one cluster, so I need to know how do you implement that? It's through what? Through Python or through C or what?
Say it again. I didn't get. Sorry, it's cut on my side.
If you want to run QS on your own cluster.
Yeah.
Exactly.
So you have multiple solution. It gives a page in the installation documentation, but either you are on a single node and you basically book the node on the cluster, because assuming that you have a queuing system on the cluster, you book just the node and you run you different simulation in parallel. I mean, whatever on this node. Either you can it give an automatic mapping of the simulation request from the G2S to the standard queuing system of the cluster, because in fact in the G2S stuff it gives like more than what we show today. For example, if you have like long simulation or big one, you can just send them to the server and you close the computer, and tomorrow morning when you are coming back to the office you check the results. I mean, if you have like 30 minutes or 1 hour simulation and you need 10 or 100 of them, you don't want to wait leaving the computer connected to get the output. So in fact, you just have like a ID for each task and you submit all the tasks and you can retrieve them later. All this is in the documentation, but that's the way to, and if you have issue, just send me an email. But yeah, that's the way to go when you go to cluster. In fact, you submit all the job, and once they're finished, you recover them. But when you recover them, it's transparent. It's still in your Python or MATLAB code. It's, you don't have to submit the job in the cluster and everything. Once you finish the installation on the cluster, it's totally transparent when you use it on your own laptop. So when you submit a job, the job will go to the cluster will execute it, and after you will retrieve it in your current laptop.
Okay, my question on the cluster itself. I mean, here, do you use the MPI to distribute the work between the nodes, or it's
single node? In fact, we have a solution, but we currently don't provide it. I mean, if you have such big need, let me know, and we'll be happy to work on to make it working for you. But we use 0MQ behind to make the communication, and until today, we basically with GPU we were fast enough that we didn't see the need of parallelizing over multi nodes.
So you don't have this large data set that's need more node, you mean?
Exactly. We never reach this point, having big simulation were big enough, such as it's like not feasible in a reasonable time, and we need like multiple nodes to make it. But if you have such issue, let me know. We'll be happy to provide an easy solution to fix this.
Okay, thank you.
Welcome. So if no one else has any other question, I will maybe continue with the more advanced simulations. So, so I start with the gap filling that Fabio just explained before. But before this, we need a function to display. And as it was written in the chat, we can increase the size of the figure with big size, fixed size, and feel free to make it bigger if you have a big screen, or to make it smaller if you have a small screen. So in this case of gap filling, we will use a very well-known in the MPS field an image with the Bangladesh image. Maybe Grégoire, you want to say some background about from where this image is coming?
I showed something similar in the presentation. It's a river. It's basically a river.
It's a river
in Bangladesh. The Ganges River. Yeah, but no. I can say more. This in what I showed was a binary image, black and white. And what has been done here is that we generated 2 Gaussian random fields and we cookie cut them. one in each category, just to have something a bit more continuous and realistic. But that's synthetic.
And naturally, the origin is like a complete image, but we make a gap in that is full of none, and that we are trying to fill. So as Fabio say, it's as simple as putting the image for the both parameter, for the DI and the TI. And so I provide like, I put like k equal 1,2 because I just did test and it was looking good. N equal 50, usually for 2D, N equal 50 is a good starting. And acceptable big kernel with full of uniform, so in fact it's not very useful. And here we use the CUDA flag to go a little faster because 2D usually take much more time that 1D, so that we don't lose time on waiting for result. We can just use the CUDA flag. So that the simulation much quicker and it's look acceptable. And if you run again, you will get another simulation.
You can also set the random seed to have to reproduce always the same simulation.
So it reproduces the same simulation on the same machine. For example, if you remove the CUDA flag, is possible, or you add it, it's possible that it change. But each time with the same set of flag, it will give you the same result on the same machine. Because sometimes we don't have control on the random generator. There are sometimes varying regarding the compiler implementation and so on. So we cannot guarantee that you will get always exactly the same results if you change of computer. So that's typically a gap filled situation, which look pretty good, but usually a single one is not very relevant. So we want like multiple simulations. And here is the moment where the CUDA flag is really coming in as an interesting parameters, because the same simulation take like 1 minute, and I don't want that you lose time 10 minutes waiting on simulations. So we can use GPUs. And so we are interested in 10, yeah, 10 look good. We're interested in two stuff. So the mean to know like the E-type, what is the most we say probable, and the distribution to know where we are certain and where we are uncertain. To know if like in a given place we always have the same value, that means we are very confident that there it is value. So that's the mean that you get. So you see that around the border, the value are very either blue or green, you know, yellow, green, you know what the value are. When in the middle is a little of everything and you don't really know what is going on. And this is reflected in the deviation for each pixels. So you see that on the border where you have enough data to constrain the simulation, you are very certain about what is going on, but very quickly in the middle you have a little of everything with possible. What can I say more? So if you do more simulations, this will come even more uniform. Here we have only 10 simulations, so you still have like some artifacts inside of the simulation. So usually we use this, and after we apply like typically a transfer function on the top of it, and that's the reason we need like proper structure. If it's just to get the E-type, is a little waste of resource to use MPS. This is a simple case in 1D. Naturally, this can be used in multiple variable too. So in this context, it's similar. It's exactly the same example as this one shown by Grégoire in the presentation. So we have this Landsat 7 image with gap. So I don't know if it's exactly the same image. I think it's exactly the same.
Yeah, I think it is.
So this image is provided with like 5 bands. We have like the blue, green, red, near infrared and shortwave. And the idea is to fill all these gaps. So you can check how look the other bands by just changing here the value in the display. Feel free to play around with that. Here we can run the simulation. Maybe some comment about why suddenly the way of loading data changed. I don't know why, but in Python, I didn't figure out how to make the load in a single line. I didn't find any TIFF libraries that can load a multivariable TIFF directly from internet without storing the file. Someone knows the answer, would be happy to fix it. So that's the results. So don't hesitate to put a bigger fixed size here. For example, I will do it. Put like, let's go for 40. So you can really zoom in the image. Mistake, I run again the whole code.
Yeah, one comment, maybe the order of the bands. If you want to display it, I think it's always RGB, so red, green, blue.
No, they're blue, green, red. That's the reason it gives this fancy -1. That because the displaying lib require RGB, and we get it in blue, green, red. So
oh yeah, okay. So
we basically
like
put.
So this
Yeah.
is 210 actually.
Yeah, exactly. That's 210.
Okay.
And that's the result. So we can still see some artifacts by the bands where we fill it, but globally it's pretty good where the fields are pretty continuous. And again, depend of value. You can play around to try to find a better value. The kernel can be smaller usually for this type of problems because the gaps are not so big. So no real interest to go very far. Number of neighbors typically can be smaller too, but not too small. In other case, you go in unstructured results. I don't have a lot more to say about this. Typically, simulation are a little more noisy than original data. Can be an issue for some stuff, and for some other, it's not so critical. But in other cases, post-processing is very common to use a median filter or something like that to just remove the crazy noisy pixel. Let's put an example of colorization. So here the problem is the following one. We have similar images, but assume like suddenly the color part of the sensor, like the RGB, is broken. So it's totally artificial, but assuming it can happen. And we would like to recreate this variable. Can we do it? And this is a very complex problem because the two other bands that we get that I just display here in a fancy color are very uncorrelated. I mean, it's not the uncorrelated. I mean, the relation is, yeah, uncorrelated is the word. The relation is very not easy. I mean, for a given green, we can have many near infrared value, and for a single near infrared value, we can have so much green. It's like really hard to make a link on the pixel. So the idea here is to use the MPS to take in account the spatial structure of this value to get the original value back. Maybe I show always the scatter plot with the green, but just maybe let me add few others just to show the other. We can check the green and the blue, the red and the blue too versus the green, that are much easier because they are very well correlated with the green. So that will be the blue, and that will be the red. And you see that much more predictable the green out of the blue and the red out of the blue. And here we're in a very unpredictable scenario. Especially this image was even like cut in range of value and so on, so it's a little harder. But we can still get something with, I will say, acceptable, better than nothing, definitely. So now this time it doesn't need to simulate only where we have the gaps. It doesn't need to fill only this gap, but at the same time, you need to find the RGB color for each other pixel. So it takes much more time. In this case, I didn't take the motivation to fill first the gaps. I straight away moved to do everything together because it doesn't give real limitation on the method to do both at the same time. So just let it go.
And so the idea here is quite a common problem, is that you have in your training image, you have a lot of variables, but in the area you simulate, you have only one of them, or maybe only 2 out of 5 or something. So in here, that's a colorization problem. You have only the black and white image or the whatever color you have, and you try to generate the other colors. So you have black and white and try to create the color with each color being non-linearly related to each other.
Exactly. And what we are looking to get comparing to other methods is to still have like fields who are continuous and not to have just a random value that fits the variable, the other one, but not the neighbors. So what we want is that the forest is like globally going together and that you have fields who are continuous and so on and so on. That's what we get here. Okay. If anyone has a question, feel free to ask.
I have a small general comment for the gut feeling case. In my experience, an optimal setup for a certain data set for unconditional simulation is not necessarily optimal for gut feeling. So it means that if you find a good value for key, ki and n, to make just free simulations, no given conditional data, for the same data, maybe you have to change those values when it comes to do the gap filling.
Clearly.
Unfortunately.
That's
often the case, yes.
Yeah, that's just because in a gap filling setting, you have your training data is clearly different than if you just have a training image and you generate something. Because you have a lot of data that are at the same time giving a model structured information, but also local information. So you have different type of input to the whole problem.
Yeah, exactly.
Maybe other comments quickly about the method. So we didn't show everything was possible because we can define the number of neighbors per variable, the kernel per variable, and so on and so on. Feel free to check the documentation, and if anything, you can always like send an email, or if you have a fancy problem that you don't know how to put in the method, be always happy to help. Yeah, and after it's just the imagination with the limit about how to put the problem inside. Okay. No one has questions? We're almost at the end of the time. We say until 4 now.
Yeah, we said until 4, so we're really on time.
So we still have 10 minutes. That's good, huh?
I have a general question about this gap filling for when you have like cloud cover. I mean, there are many methods in the literature, right? So Reinhard Fuhrer at the University of Zurich has some method, and there are many others. Have you tried to compare? I mean, is this going to beat any of these existing methods, or do you know?
It's always hard to do a benchmark because we didn't try. First, we didn't try. Maybe we should, but a real benchmark to have it done properly, you need to put all the people on the same problem, and everyone runs his own method. Because in any case, you have a step of inference. If it's someone else doing it, you will mess it up. So that's a big exercise. We would like to do it, but it didn't happen. But yeah, that would be a nice project.
Yes.
And after you have a lot of variation, like some method require to gap filling from that the training data are the same area, and some other doesn't need this. Typically, this approach doesn't require that you have a same image in same area, but it makes uncertainty about the place you are feeding. You don't know what is going under. And if we could beat it in quality with the good settings, maybe we will definitely not get it in like computation time, because we will make a lot of computation were not needed because it's this specific case, and you know that basically the pixel you need to find is just, I mean, at the same location in another image or something like that. And it's possible definitely to redesign a part of this method to get probably similar performance, but like as it is, we will not reach the same computation time.
Yes.
We did some comparison with other methods in other settings that the cloud thing. For example, for this exact setting of the gap filling for Landsat 7, the same thing, we compared to a bunch of other methods that do exactly the same problem. So some of them are based on various, I mean, flavors of kriging, with covariate, with no covariate, and so on. And in the specific setting of this one, the MPS was the best. In terms of structural accuracy, it means that you have a gap, you try to find out what happens in the gap, you get the right connectivity and the right features. Sorry.
That's so funny.
Okay, I'm muting the person. So you get the right type of structure in the gaps. Like we showed, we cannot see the difference. Other methods that would blur the inside of the gap, they would have a better accuracy in terms of root mean square error, typically. If you just take the average on both sides of the gaps and you put the value there, it's all smooth. But in terms of RMSE compared to the truth, you're better. So then it's hard to assess which one is the best. You have to look at what type of structure, what type of connectivities you have. And yeah, it's really hard to do a proper benchmark, you know, but we did it for this one. We also did it for downscaling. We compared with other methods. Just downscaling is a bit complex. You need to have a secondary variable at the coarser scale, which you try to downscale. And this also, we could have very good results. But we did not do a specific benchmark for the case of clouds. Because clouds is a bit different because you have one huge missing area. Here you have many tiny ones. So if you have one big gap, what happens in the center, you have no local accuracy in that. You cannot expect any local accuracy. It's only about structural accuracy.
And in terms of computation, how does this scale up? So if you have really big images, like 1,000 by 1,000, you have a million pixels, you can do that? Yeah. Or?
So 1,000 by 1,000, we're in the 1,000 by 1,000 area already with this one. And you see it's a few seconds. But if you have millions by millions, yeah, Mathieu?
Yeah, so just like mathematically, we can answer to this. So the computation increase in n log n for regarding the training image, and it increase linearly in n for the simulation size. So after, if it's big, it just takes more time. Multiple training image is more efficient than a big one with a lot of gap inside. So if we have like two areas, typically, it's better to provide two training images to the algorithm than providing a big one with a lot of none between them to make the image. So yeah.
And also I was starting to answer the question of Wang, but the long essay, but it's orally. MPS outperforms kriging when the data is not really a random process. Actually, it is geostatistics. So data is always considered as a random process, but MPS performs better than kriging when the process is too hard to model with the Gaussian process or some kind of controlled random process. If it's too hard, like this image, it's going to be really hard to model it with the multivariate 5 variable spatial field because there's too much complexity. So then you give up and you go with MPS. If you can model it with the Gaussian process or with any transform of it, go for it. It's going to perform better. You are going to have control of your uncertainty. You're going to have control of your parameters. You can infer everything properly. You have a whole framework. That's better. But in many cases, with this kind of data, you just cannot. And then you have to use MPS.
Yeah, I think here there are just too many discontinuities and like that. I mean, you cannot have a realization of a Gaussian process that gives you something like the image here. So
yeah. Or I don't know, then it's not a Gaussian process. Then it's
right.
something else, but we don't know.
Yeah, and it's a little more robust to non-stationarity MPS because if we scan always the image, we can potentially put stuff from one side to the others, even if it's not trivial. But we can more or less do it. And when in random process, usually you do this hypothesis, or either you have a covariable to fix it.
I think also something for many years, the people had this discussion, is MPS better or is covariance better? And this is the wrong question. It's just, we have a toolbox, many tools, and it depends on the problem you have, because all this is tools to help us understand things. So here, what we do, we don't infer much. We can calibrate parameters, but we don't really infer, but then we can generate data that help us, for example, in a process where you need data, continuous data as input. You have a land cover model that needs a continuous image, so you need to fill your gaps. Or you have a hydrological model that needs as input a continuous time series. You cannot have a gap. You need to put something in there. This is when it's useful. If it's just an estimation problem and it's a Gaussian process, of course, that's totally different. So it's just one more tool in the toolbox. That's how I see it.
So maybe one last comment, just I think about it. If you are using on your own computer, you can at the end shut down the server remotely. I mean, from inside the code using this function, and it just kills the background process. It just to have a little more clean computer that no random stuff are running. But here on Jupyter on GitHub is not needed. I just put it for information. Okay, I think we are running at the end.
Yeah, Wang, yes.
Question?
Yes, well, you're right, Wang. I mean, it's an open problem. What we quantify is variability. It's not really uncertainty. Although, I mean, we have anecdotic examples that, for example, if we model a Gaussian process with MPS, you can generate a huge training image that is a Gaussian random field and use it as training image to make simulation. You end up with the variability that is not too far from the expected variability of your random field, given the right parameterization. So if you parameterize correctly, you get something that is not too far, but we cannot prove that we have the right uncertainty because we don't really have a model.
Yeah, I think we're right on time. So I would like to thank all three speakers. I think it was a very interesting presentation and very useful for everyone to learn about this techniques. So thanks very much.
Yeah, thanks to you for attending. And so the part that has been recorded means everything, all the practical part. I will put it. I will put a link to it, I think, on GitHub, on the same GitHub I sent. I'm not able to put the video probably because it's too big, but I will make it available.
Okay, good.
Okay.
Great.
So see you tomorrow, everyone.
Yes.
For the next part. Looking
Yes.
forward to that.
That's good. All right.
Have a nice day.
Yeah. See
Thank you.
everyone.
Bye-bye.
Thank you.